speaker is Juani Bermejo Vega from the Free University of Berlin, who is going to be talking to us about quantum devices for outperforming classical computers.
Hello. Hi. Hi, everybody. Good morning. So it's my pleasure to be here. I would like to thank the organizers and all of you for putting together this great event. I'm very excited to be here because it's my first time ever in BQIT, also my first time speaking in Bristol. So I look forward to the workshop and the discussions. I'm also going to be here for 2 weeks. So if anybody wants to chat after the talk, just grab me or send me an email. I'm going to be talking about quantum devices for outperforming classical computers. And I'm a theorist. I'm going to be focusing on practical aspects of these 2 papers that we have over here, mostly on the first, which is joint work with Dominic Hang-Leiter, Martin Schwarz, and Jens Eisert from Free University of Berlin, and also Robert Rosendorf from UBC, Vancouver, Canada. Okay? So anyway, I'm going to be explaining what these little squares and circles mean during my talk. So maybe let's start. It's left or right?
I have to get a bit closer.
Maybe I have to get closer.
Is it like this?
Or you might need the correct.
Maybe I picked the wrong one.
I'll plug that one.
I did say
Oh,
I did say to
look, now it works. Thank you, Viv. That was a great contribution. Okay, so this talk, in a snapshot, I'm going to be talking about, well, the question that guides this work is basically what and when and in which sense can we hope that quantum simulators will provide some sort of computational advantage or quantum speed up over classical computers. Our main motivation is to find ways to use quantum devices to demonstrate quantum computational advantages, more precisely to realize in the laboratory quantum devices that show such advantages. So we want to actually demonstrate is the device itself. But as we all know, many of us are working on trying to build quantum computers, but this is kind of hardish. There are many engineering issues, and there are challenges to build universal fault-tolerant quantum devices. So they're not here yet, but already, as we speak, there are many laboratories that are very good at engineering synthetic quantum systems, sometimes called quantum simulators. We would sort of like to find out whether these devices are good for demonstrating some quantum advantages. So this is the main motivation for our work. And that's right, should be left. Okay, so now on this area, what's out there, what can we use, what are the main approaches? I'm going to be mentioning a few works, but not all of them, but let's start. So on the first hand, we have a community in quantum computation simulation that are building so-called quantum simulators. So this is a very broad area, but briefly, generally speaking, what they do is try to engineer a quantum system directly on the laboratory, realize something like a Hamiltonian, and it's not so focused on gates and error correction. So, and an example of that are these, for example, these works from the cold atomic community in optical lattices. What they do is they build optical lattices in 2D. They trap a bunch of atoms or local systems in their lab. They're fairly well isolated, and they can engineer Hamiltonian evolutions, run them for some time, prepare some input product states, let them evolve, and then measure. And examples of such experiments are conducted in here using several thousands of atoms, and they can engineer these Bose-Hubbard Hamiltonians. And actually, this works over here, which is something that we really had in mind when we started this work. They push these quantum simulators to the extent that it becomes hard to classically simulate them with current classical algorithms based on tensor networks, such as DMRG. So now, when we look at these works, we are interested in asking the question, is this a fair demonstration of quantum advantage? And before any of you answer, I want to have a spoiler. There is a person who is not very happy, which is this cat. Now, this cat, I mean, he's obviously sad, right? Like, this cat is a complexity theorist or a theoretical computer scientist. So, and it's kind of pissed because, I mean, this is a very nice and great work, but it's comparing a quantum algorithm versus a classical algorithm. Now, in theoretical computer science, what we like to show or find evidence is that there is no other possible classical algorithm that could, in principle, compute the same task. So that's when we say, oh, there is no classical algorithm whatsoever for the same thing. That's actually what we want. And these works are not in that direction. They are more in the direction of developing, showing practical quantum advantages for some practical problem. And we're interested in this most rigorous theoretical computer science setup. And we want to make this guy happy. Okay, so now there is also the quantum computation more formal community. So there is people now trying to build noisy intermediate scale quantum devices, and a section of the community tries to use such devices to demonstrate quantum advantages in a more formal sense. And an example of those is this celebrated boson sampling paper by Scott Aronson and Alex Arkhipov. So what they show is, well, they take something really simple, which is they consider linear optical quantum circuits with photonic inputs. They plug some photons inside. They run some linear optical quantum computation, and then they measure everything. Okay, so that's fairly simple. It's not a universal quantum computer, and it's pretty close to something that you could in principle realize in the lab. And they show something quite interesting, which is that based on some known complexity theoretic conjecture, which is the collapse of the polynomial hierarchy, that's some studied conjecture in theoretical computer science and a generalization of the P is not NP conjecture. Well, they show that if that conjecture holds a few others which are plausible, then it's impossible to classically simulate such a device in the lab. So many of you here work on photonics. I guess you are pretty familiar with this. What we like about this work is that it connects a harness, the harness of a task to a known complexity theoretic conjecture. There is another approach, also quite popular today. It's by people in Google Research. They do something similar to they want to build something similar to a boson sampler, except that it uses qubits and regular gates. So they start some qubits on a standard basis state, and then they do a regular standard quantum circuit of local unitary gates, but they pick these gates at random. So it's kind of similar, but these gates can be 2-qubit, single qubit gates. And they have similar hardness arguments as in the boson sampling paper. They want to realize this as a sort of test for quantum advantage. Now, how do these things put together? So how do they compare? So on the one hand, we have these quantum simulators that I mentioned. So the nice thing about them is that you can actually make them pretty large these days. Like, for example, these atomic set systems, they have thousands of degrees of freedom running in there. What we don't like about them is that they're unhappy cat. There is no harness proof which connects to theoretical computer science for them. And then we have several approaches for demonstrating quantum advantages in this NISQ community, like the boson sampling, also IQP circuits, which is another proposal. There is people in Bristol here, like Ashley Montanaro, I think you're over there, Ashley, who have worked a lot on this. Random quantum circuits. The good things of these approaches is that we have strong harness proofs or strong harness evidence that they are hard to simulate classically. And there is lots of disadvantages. All of these approaches so far have not been realized, and it's actually challenging to make these tests. Like, there are lots of engineering issues for scalability, as you know. This proves implementing this quantum advantage test requires, not crazy, but relatively high fidelities, relatively good control. Implementing them, that's just not trivial. So we are not there yet. We are pushing it. Like, there are different communities trying to do this. Another issue is it's actually quite hard to verify that these protocols are working. And the main problem is we don't have quantum error correction running yet. And most approaches for verification for these systems run in exponential time. I will go to back this later in another slide. There are also some efforts trying to make these approaches closer to physics, like to these, for example, quantum simulator setups, but they rely on pretty complicated and physical Hamiltonians, which are not quite translation invariant. What we would like to do in this talk is try to combine advantages of these two worlds and sort of apply this sort of machinery to these quantum simulation devices. Okay, so from here on, I will start talking about our contributions. So what we want to do is, as I said, take these quantum simulators and try to build some nice tests of quantum advantage based on them with something simple, ideally as simple as this question over here. So in our paper, we introduce some protocols which are basically based on time evolutions on a 2D lattice of certain Hamiltonians which are translation invariant. So we look at very short time evolutions of translation invariant Hamiltonians, and we have different, did I lose the laser? Okay, I lose the laser. We have different protocols. In the talk, I will focus on the first one. The main differences are that they rely on different types of product state preparations. So, and I will detail one of these protocols that we have. So the thing that we do in these protocols is we start in some product state. Like we have a lattice, 2D lattice, square lattice. We put some qubits into that lattice, and then we prepare some random product state, typically. So in this particular protocol, we just initialize every qubit to a superposition of 0 and 1 with some little phase over there, which is not too important for the talk. But we put some phase. And after that, we do a quantum quench, or we do a short Hamiltonian unitary time evolution with a time-independent Hamiltonian, which is this Hamiltonian over here. It's a commuting, pretty vanilla Ising Hamiltonian with interactions on the edges of this graph and local fields on every side. So you just time evolve these qubits under this Hamiltonian for some constant time, and afterwards you measure absolutely everything in a fixed basis. We pick this to be the sigma x basis, or basically we do a Hadamard gate and measure everything in the standard basis. And this is the end of the protocol. Once we are here, we just collect a bunch of numbers and we just accumulate these numbers in our computer. Of course, we're generating this with some probability distribution. Okay, so what we like about these protocols is that they are fairly close, and we think they are motivated by people, by experiments. So our protocol has 3 steps, and each of them has been realized independently in a different type of collatomic setup. So the first 2 steps have been realized in collatoms. They have prepared random product state evolutions using hyperfine encodings. They have also implemented this Hamiltonian actually a long time ago, and also using hyperfine encodings. And in fact, this experiment is actually motivated the beginning of this other field called measurement-based quantum computation, because they also exploit this Hamiltonian. So we want to reuse it. They have realized this similar, so they can actually also do today single-site microscopy. They can resolve their entire optical lattices and detect where atoms are. And the challenge to build the full experiment as per today is that the these different packages that I am explaining here, they are not using the same qubit encoding. So the main challenge at the moment for realizing this protocol in optical lattices, for example, would be to kind of combine something like single-site microscopy with the first 2 steps. Okay, so it's not super trivial yet, but we think it's still quite in the spirit of what these synthetic quantum systems can do. And also you could, in principle, realize this with other type of setups like, I don't know, maybe ion traps. Okay, so this is the end of my description of what the protocol is. And now I'm going to move towards what is hard to simulate in these protocols. So we have this main result. And what the result says is something analogous to what you find in the boson sampling paper, but for our architecture. So what we show is that generating numbers from the probability distribution of the quantum computer is actually hard, assuming some complexity theoretic conjectures. And in fact, we are actually using very similar complexity theoretic conjectures to the boson sampling paper or the IQP setting or this random quantum circuit proposal by the Google Research Group. So what the result says is that sampling from the output distribution is difficult in principle, and the conjectures that enter this argument are this fact about this so-called polynomial hierarchy being infinite, which is what was introduced in the paper of Aronson Arkhipov, and also early by, actually this is the wrong reference. It was introduced by Brenner and Josa and Shepard, but also Brenner and Ashley and Shepard have a recent paper on this. Okay, and then there are other 2 hardness arguments that enter these claims. I'm not going to enter a lot into the complexity theoretic aspects of this proof here. I'm giving another talk next week in this quantum computation theorem practice workshop, and I will be talking specifically about these 2 conjectures. But for complexity theories around, just wait another week, please. For the rest, so again, this is kind of in the similar spirit as in boson sampling. For this harness result to hold, we need to assume that when we look at probabilities of our setup, and we pick one at random, they will all be comparably hard to compute. So we are assuming something that we call average case harness. Okay, this means if you take a probability, okay, maybe one of them is actually, we actually can prove that some of these probabilities are very hard to compute rigorously, but what you need for these tests is that all of them should be more or less comparably hard to compute. Another conjecture that enters these arguments is something that people in this community call anti-concentration, which roughly speaking means that the probability should not be too peaked. Okay, so next we have actually done a lot of progress proving these conjectures. Also, other people in parallel have proven analogous conjectures for different setups. So next week I will be talking that we can actually prove this thing called anti-concentration, and we can prove a version of the average case conjecture that we are using in these papers when we don't have errors. So I will talk about that and connections to TD signs, Hamiltonian gaps, and quantum cellular automata. And for the rest of the talk, you can forget them if you are happy with the following fact. So these two statements, we need them for the errors. Like if you don't want to believe them, the same theorem will hold, but you would need to sample exactly from the output distribution of the quantum device. With these two conjectures, we can get some epsilon constant robustness, which is nice for realizing the experiments. Okay, so that's the heart of the complexity theoretic part of the work. And now I'm going to move to something which is more practical, like if you realize these protocols, how do you make sure they are actually working? So there are lots of challenges for verification in these noise intermediate scale quantum devices, starting with, for quantum advantage proofs that we are looking at, they are based on these problems which rely on sampling distributions. And I briefly mentioned these distributions that are typically quite flattish. So this makes verification of them quite hard because they are fairly unstructured. There is ongoing work, for example, by Handleiter and others, showing that just doing classical verification based on classical samples might take exponential time. So it doesn't look easy. We also have a challenge that we cannot do much with available quantum hardware. Like there are protocols out there in the community that are based on delegated quantum computation, blind quantum computing, interactive protocols. Most of these protocols cannot just be realized near term. So we have some operational restrictions, actually many of them. Standard tomographic methods also are exponentially costly or compressed sensing. And what people in other approaches, like in this Google type of setup, are doing is sort of like introducing some additional assumptions on the noise model or some additional complexity theoretic assumptions, like in this interesting work of Aronson and Chen. So with these works, what they show is that with some additional assumptions on the noise or complexity theoretic arguments, then you can do some hybrid verification which requires only a polynomial amount of quantum experiments and some exponential classical post-processing on top. So it's not efficient, but you can do something sort of in the middle. And we will, in this work, we do some sort of extension to this type of work, like this type of approach, number 4. So we can use some verification methods out there to show that it's possible to verify the type of experiments we are doing if we have more or less actually good single qubit measurements. So if we have some quantum resource, reliable quantum detectors, reliable single qubit measurements, we can show that we can verify our quantum computations in precisely the preparation of the final basis state, and actually only using polynomial time. So this is a difference with the previous approach number 4. So the main difference is that everything here runs in polynomial time. And in the previous approach, they are only taking classical samples. Here we are taking quantum samples. So we measure our qubits on some basis. So this might make sense if you can, for example, test your single qubit detectors in parallel or, like apart from your quantum experiment, which might be more complex. But anyway, it's an assumption, just to be rigorous. And the protocol is based on this previous work on Handleiter, Clich, Schwarz, and Iser. In this paper, they introduce a general scheme to estimate fidelities of ground states of local frustration-free Hamiltonians. So basically, their protocol, what it does is if somebody wants to prepare a ground state of some Hamiltonian, they can do some local measurements of actually some Hamiltonian terms, and they can compute an estimate of the fidelity of the state that you have prepared with respect to their ideal ground state, also only using polynomial time, like with a classical computer. So more precisely, the scheme takes a ground state, measures some local Hamiltonian terms, the Hamiltonian terms of that ground state, and then using that, they show that the average energy that they measure of the state, like you measure local Hamiltonian terms, you can estimate the energy. So if you look at the global energy of the state that you have prepared, there is a lower bound to the fidelity based on the energy of the Hamiltonian, which goes with 1 minus the Hamiltonian inverse the gap of the Hamiltonian. Okay, that means that if you estimate the experimental average energy of the ground state that you end up with, then you can actually estimate the experimental fidelity of the state that you have. Okay, and in our work, what we do is we apply this protocol and we heavily optimize it. So the original protocol requires 4 or 5 local single qubit measurements, and we improve this to be single qubit measurements. And also we improve a bit the scaling. But what we can do is basically make different rounds of the experiment, measure single qubits, and in the end compute some average energy of the Hamiltonian. With that, we get an average, an estimate of our fidelity, and if the fidelity is bad, we can throw the experiment safely away, which is something nice, because we don't want to, when we want to claim, we have demonstrated some quantum advantage in the laboratory, we don't want to have some dirty, noisy device in there and make like a poor claim. We want to be sure that we reject badly prepared states. Okay, so with this, I would like to wrap up. So I have basically explained you these quantum advantage tests that we have, and now future directions out there. So it would be nice to work on physicalizing further these quantum advantage experiments in general, like boson sampling, random quantum circuits, and bring them closer to experimentally accessible operations. So, and here the main issue is that these experiments are coming closer and closer to what one can do in the lab, but they are still fairly hard to implement up to high fidelities. So that's, there is lots of work, quite a bit of work to do there. Now in this talk, we have focused on quantum computers that outperform classical devices for some tasks, but we are not looking at any task concretely. Any task would be good for us if there is an exponential advantage out there. But that wouldn't give you any practical quantum algorithm for a problem like factoring. So there is lots of work to do in the direction of proving similar statements, but for problems of more practical interest, like maybe something in condensed matter theory or in optimization. Okay? So there is work to do on proving these hardness conjectures, and actually I haven't gone into that detail, but there has been a lot of progress in the last years proving versions of these conjectures. And what it stands right now is that there is some missing approximate average case conjectures entering all of these proofs, which are very, very hard to achieve, that require techniques like robust polynomial interpolation to be developed in the theoretical computer science arena. So if you're a theoretical computer scientist and you're around and you want to talk after during the coffee break, then just grab me. And there is a lot of work to do building better, faster, and more secure verification protocols for boson samplers, our devices, and random quantum circuits. The main approaches that are feasible right now normally require either exponential processing in a supercomputer or some assumption on the noise. So it would be nice to bring such verification protocols closer to device independent. Yeah, so you're a device independent person, and you're out there, then just let's talk later. Okay, so with this I would like to conclude my talk. So if you want to remember one thing, I showed that some simple quantum simulators are hard to simulate classically, and they are constant time evolutions of translation invariant Hamiltonians, where you're trying to use that to make tests of quantum advantage. These are the main references, and with this I would like to thank you for your attention.
I just want to check that I understand the direct. I think I call this method of checking if the fidelity is high by measuring the Hamiltonian or the energy. Direct state fidelity. No, it's not direct state fidelity estimation. This is another method. So the method that you propose requires that the ground state is the unique ground state of a gapped Hamiltonian. Right?
Yes, it's.
And so you need to know. So do you need to know that in advance, or can you go in and measure and check that it is the unique ground state of a gapped local Hamiltonian?
The protocol introduced is basically based on half-lighters and also worked by Aulita, which came before for photonics. It does require that you know that there is a unique ground state. So basically, it has limitations if you want to apply this to arbitrary quantum simulations of a Hamiltonian. If you don't know very well what the ground state is or the ground state energy, it's not a big issue for us because we actually all know all of these parameters analytically.
Right. So we did this work last year or 2 years ago called Matrix. Well, with Martin Plenier called Matrix Product State Tomography, and we demonstrated the method of doing this more efficient approach to tomography. And I'm remembering my own work now, but I think that we were able to make the statement. We found what we thought was the nearest MPS state represented by the data, and then we could go back in and use this method to check how close the state in the lab was to that matrix product state. And this was actually very, very useful. And it was exactly using the method that you presented up there.
Maybe we could discuss about this later because actually it might be useful. I didn't mention this, but the state we are preparing is a PEPS on 2D.
That's 2D. Yeah, this was 1D, what we were working on.
So it's like a 2D version of what you said. Maybe what you did can also do something.
Yeah. But I'd say basically that these methods for independently characterizing the states in the lab, I think, are very important right now because we already have states that are too complicated by our existing methods to characterize, and so I'd be interested in talking to you about it.
Yeah, I guess it would be interesting if you can push that in the direction of 2D and develop some practical verification method for 2D PEPSs. Like, that could be nice.
Okay, so this might be a quick question then. So last year there was a paper put out by Alex Dalzell and Aram Harrow on trying to figure out how many qubits you actually need in order to demonstrate that your quantum computer is better than a classical computer. So it was something like 100 and something for IQP circuits or 90 photons for boson sampling. Do we have any idea how many we would need for kind of this model?
Okay, I don't want to make... Okay, these papers introduce some other fine-grained assumptions. I'm not sure how they didn't compare it to our paper, I think, so I'm not sure how that would compare. The more pessimistic estimate, I mean, based on, for example, the Google estimates for quantum advantage that they claim they need like 50 qubits. And you might want to basically, actually, you can show that they need 50 qubits. I could argue that we need the square of that, which would be like 2,500. So based on that, which is not a big problem for example, cold atomic setups, because they have thousands of atoms right now, and they can easily trap tens of thousands. There is also a way to map our protocol to a 1D setup where you only use 50 qubits. But basically, if they have discussed how many qubits they think Google needs, I need the square. So, yeah.
Let's thank Juan.
Yeah.
So we're going to have a quick coffee break now. If any of you need any assistance with anything, you can speak with Holly in the registration area or anyone of our volunteers wearing these stylish purple shirts. And yeah, see you back in 5 minutes.
Okay, I leave everything here.